What do a bank account, a hurricane, a moth flying into a candle, and the neural network behind ChatGPT all have in common? All four are secretly obeying the same 300-year-old number. It shows up so often that once you learn to spot it, you'll start seeing it everywhere. This is the story of E. E, also called Euler's number, is approximately 2.71828. But here's what makes it strange. Nobody set out to find it. Three different mathematicians, working on three completely unrelated problems: a table for astronomers, a question about bank interest, and the geometry of a curve, each stumbled onto the exact same number without realizing it. It took over a century and one final mathematician to notice they'd all found the same thing. Rewind to the early 1600s. There are no calculators. If you're an astronomer or a sailor navigating by the stars, you constantly need to multiply enormous, ugly numbers, the kind involving sines and cosines of angles, calculated to many decimal places. Multiplying numbers like that by hand, correctly, could take a skilled mathematician the better part of an hour, and one slip anywhere in the process throws off the whole answer. John Napier had an idea that would change that forever. What if you could turn multiplication into addition? Here's the trick in one line. The logarithm of a times b equals the logarithm of a plus the logarithm of b. If you have a table that already lists the logarithm of every number, you never have to multiply again. You just look up two values, add them, and look up the answer. Let's actually do it. Say you need 245 times 3521. Instead of multiplying directly, you look up the logarithm of 245, about 2.3892, and the logarithm of 3,521, about 3.5468. Add those two, 5.9360. Now look up which number has that logarithm, the antilog, and you land on approximately 863,000. The true answer is 862,645, close enough for 17th century navigation and dramatically faster than direct multiplication. Here's the part that actually matters. Calculus didn't exist yet. Napier couldn't take a derivative if his life depended on it. What he really did was purely mechanical. Pick a ratio just a hair less than 1 minus 1/10,000,000th. Multiply by it. Then multiply by it again and again. Each step shrinks the value by the exact same tiny fraction of itself. Do that by hand for 20 years, and you get a table. Now here's what Napier had no way of seeing. Take that same move, 1 minus 1 over some number n, raised to the power n, and watch what happens as n grows. 2, 10, 100, 1,000, 10,000. The result keeps creeping toward one specific number, 0.3678794. 1 over e. And Napier's own ratio was built on n equals 10 million. So what happens if you follow his sequence out exactly 10 million steps, matching his own number? You don't just get close to that limit. You basically land on it. 10 million times 1 minus 1 over 10 million, raised to the 10 millionth power, comes out to 0.3678794, accurate to 7 digits of 1 over e. Multiply that back up, and 10 million divided by e is about 3,678,794. Napier didn't engineer that. It's an accident of arithmetic, forced on him the moment he chose 10 million as his scale, and it was sitting, unnoticed, in his own hand-built table. In 1618, an appendix was added to Napier's book, likely calculated by William Oughtred, containing a table of these logarithms, row after row of ordinary-looking numbers. Nobody at the time thought of a logarithm as being to a base. That idea hadn't been invented yet. Remember that row we just worked out, 10 million, divided by e, about 3,678,794? Go looking for it in the real 1618 table. And there it is, sitting quietly among row after row of perfectly ordinary-looking numbers. Divide 10 million by that row's input, and out comes 2.71828. He was here the whole time, decades before anyone had a name for it. Now jump forward to 1683. Jacob Bernoulli isn't thinking about navigation at all. He's thinking about money. Specifically, if a bank pays you 100% interest per year, an unrealistic rate, but it makes the math clean, and you start with 1 rupee, what happens if the bank compounds that interest more and more frequently? Here's the general formula. Your final amount equals your principal times 1 plus the rate divided by n, raised to the power of n times t, where n is how many times per year the interest compounds. Bernoulli's version was the simplest possible case. 1 rupee, 100% rate, 1 year. That collapses down to just 1 plus 1 over n to the power of n. Compound it once a year, and you double your money, 2 rupees. Compound it twice a year, 2.25. 4 times a year, 2.4414. Monthly, 2.6130. Daily, 2.7146. Every hour, 2.71813. Keep going, faster and faster, infinitely often, and the number doesn't explode to infinity the way you might expect. It creeps toward a ceiling. That ceiling is 2.71828. E. This was the first time in history a number had ever been defined purely by a limiting process, not as a ratio, not as a root, but as the destination of an infinite journey. Bernoulli didn't name this number. He had no idea it connected to logarithms at all. He'd simply found the same constant that had been hiding in Napier's navigation tables 65 years earlier through a completely unrelated question about money. Why does this converge instead of exploding? Expand 1 plus 1 over n to the power of n using the binomial theorem. Each term in that expansion can be rewritten as 1 over k factorial, multiplied by a string of fractions. Take the k equals 3 term, for instance, each fraction very close to 1, and getting closer to 1 as n grows. In the limit, as n goes to infinity, watch these two fractions. At n equals 10, their product is 0.72. At n equals 100, it's already 0.9702. At n equals 10,000, 0.9997. Every one of those fraction terms becomes exactly 1. So what's left is just 1 over k factorial, summed over every k from 0 to infinity. This series is remarkable because it converges incredibly fast. Factorials explode. By the time you're adding the term 1 over 13 factorial, you're contributing less than 1/10 billionth to the total. This is exactly the tool Euler would later use to hand compute e to 18 decimal places, decades before anyone had a mechanical calculator. Now generalize this beyond Bernoulli's toy example. For any interest rate r, compounded continuously over t years, the same limiting process gives you final amount equals principal times e to the power of r times t. This one formula, a equals p e to the rt, is the exact formula banks, bonds, and financial models still use today for continuous compounding. So far, E has shown up in a navigation table and in a bank account. Here's a third, completely different route, pure geometry. In 1647, Grégoire de Saint Vincent and Alphonse de Sarasa were studying the curve y equals 1 over x, a hyperbola, and they noticed something strange about the area underneath it. If you measure the area under this curve from x equals 1 out to some point A, and call that area of A, here's the strange part. The area out to a times B equals the area out to A plus the area out to B. That's the exact defining property of a logarithm. Log of a times B equals log a plus log B. discovered purely by measuring area under a curve, decades before calculus even existed as a formal subject. In modern notation, we write this area as an integral. The natural log of x is the area under 1 over t from 1 to x. Huygens, in 1661, used exactly this geometric idea to numerically compute what, in hindsight, is the base 10 logarithm of e. He never named e as a number worth caring about. He was one calculation away from discovering it and didn't realize it. So here's a fourth definition of e, totally different from Bernoulli's limit. E is the unique number where the area under 1 over t, from 1 to e, is exactly 1. Not approximately, exactly. Here's why this matters beyond just being a cute coincidence. Since the derivative of ln x is 1 over x, if we define the exponential function as the inverse of the natural log, a quick calculus rule tells us that this exponential function is its own derivative. In other words, the area-based definition of e and the function that never changes when you differentiate it definition are provably the exact same object, just approached from two completely different directions. By the 1720s, this number had appeared at least 3 separate times, and nobody had connected the dots. Enter Leonhard Euler. Around 1727 or 1728, in an unpublished paper about the explosive force of cannons, Euler started using the letter e for this constant. The first time it appears in a surviving letter is in 1731, written to his friend Christiaan Goldbach. The first time it appears in an actual published book is 1736, in his work Mechanica. Euler didn't just name the number, he tamed it. Using the rapidly converging series from Bernoulli's world, he hand-computed e to 18 decimal places. No calculator, just factorials shrinking fast enough that, within about 15 to 20 terms, every added digit was already correct. Here's where things get genuinely beautiful. Euler knew 3 separate infinite series, one for e to the x, one for sine of x, one for cosine of x, each provable just by repeatedly differentiating at 0. Watch what happens when you substitute x equals I theta into the e to the x series, where I is the imaginary unit, the square root of -1. Here's the key. The powers of I cycle in a loop of 4. I squared is -1, I cubed is I to the 4th is back to +1, and then it repeats. Every time an even power of I shows up, you get a real number. Every time an odd power shows up, you get an imaginary one. Sort the terms by real and imaginary, and the series for e to the I theta splits cleanly into exactly the cosine series, plus I times the sine series. This equation has a gorgeous geometric meaning. E to the I theta doesn't grow or shrink at all, it just rotates. As theta increases, the point e to the I theta traces out the unit circle in the complex plane, one full loop for every 2 pi of rotation. Now set theta equal to pi, half a turn around the circle. Cosine of pi is -1. Sine of pi is 0, so e to the I pi equals -1. Rearranged, e to the I pi plus 1 equals 0. 5 of the most fundamental constants in all of mathematics, e, I, pi, 1, and 0, one connecting every branch, growth, rotation, geometry, and arithmetic itself, all in a single equation. 2 final landmarks before we leave the origin story behind. In 1737, Euler proved E is irrational. It can never be written as a simple fraction of 2 whole numbers. And in 1873, Charles Hermite proved something even stronger. E is transcendental. It isn't even the root of any polynomial with whole number coefficients, no matter how large the polynomial. That result mattered enormously. It meant it could never be constructed using classical compass and straightedge methods, and it directly opened the door for mathematicians to prove, just 9 years later, that pi is transcendental too. Finally, definitively closing the 2,000-year-old dream of squaring the circle. So, for mathematicians, for completely different starting points, a navigation table, a bank account, the area under a curve, and an infinite series, and every single one of them landed on exactly the same number. That's part one. Now let's see why this number refuses to stay confined to pure mathematics.